So what I'm going to do now is give you just a brief overview of the HPE CRAY programming environment, which is essentially very similar to the what used to be the CRAY programming environment. We've just put HPE in front of it. And this is on behalf of the CTO office and also the PE team, who these extra names on the bottom of the slide here for folks who are in charge of the programming environment and getting all of this together and getting it up and running. And so as you heard from Owen, UCL have been working on getting CPE up and running on their software stack, and it looks like progress has been quite reasonable so far, so that's very good. And I'm going to give just a very quick introduction to what exactly the CRAY programming environment is, or CPE, we typically call this for short, and some of the what it can do for you. So in general, CPE is a software stack for HPC application development. It's a scalable, integrated environment. So we have from sort of compilers to scientific libraries to tools for profiling and debugging, support for a variety of architectures, all focused on being able to build HPC applications and run them at scale. And this environment has been developed over many years through close collaboration with customers, and really with a focus on real HPC applications, not just benchmarks. So sort of small picture overview of what we have here. You have support for application development, so that's your compilers for C, C++, Fortran. You have I/O, scientific and math libraries. We have MPI, a deep learning plugin. Then on the debugging side, we've got a comparative debugger, stat, other tools for analyzing abnormal termination processing, ATP. We have GDB and Valgrind, and then some nice performance analysis, porting, and optimization tools. So we have quite a good environment for developing, debugging, analyzing, and optimizing applications for production supercomputing. And the remainder of the slides are going to go into a bit more detail about what exactly we provide. So one of the big things is a consistent environment. So we provide you access to multiple vendor tool chains, so many different compilers for different architectures through a consistent environment that can automatically use our math, scientific, and communication libraries without you having to really do much. So assuming you're using the CRAY compiler wrappers, these types of things are used automatically. And then you can also use our debug and profiling tools with the chosen compiler. And so it allows you quite a quick and easy way of swapping between vendor programming environments while retaining this sort of integration to the CRAY software stack. Now, this picture tries to capture basically everything that's available in CPE, and the color coding here indicates what exactly is HPE authored, what is third-party authored, but we have some added value. We've modified, extended this somehow, and what exactly is just third-party. And so we've got support for a variety of different programming models. We have CRAY MPI, SHMEM, OpenMP, OpenAC, support for AMD, HIP, and CUDA, UPC, Fortran co-arrays, global arrays, this type of thing. Support for different programming languages, C, C++, Fortran, Python, and R. Our contribution there is our compilers for C, C++, and Fortran, and our support for the different programming models within those. Various optimized libraries, libsci, LabPack, all these types of things, FFTs, etc. We then have different tools for debugging, so your comparative debugger, GDB for HPC, Valgrind for HPC. I'll talk a bit more about those later. Performance analysis and optimization tools, so CRAYPAT, what this used to be called, now it's just PAT. The visualization tool and code parallelization assistant, which you would have perhaps previously known as Apprentice 2 and Reveal. They're currently just called visualization tool and code parallelization assistant. And then, of course, your environment setup and runtime, so enablement for different build tools, et cetera, and so these are all supported across our supercomputing lines. That includes HPE CRAY supercomputers, but also Apollo 2000s and Proliant systems. And so in terms of language support, I think we're currently at C++ 17 and the C++ compiler. I think they aim to be up to date to the current standard by the end of the year. OpenMP, we're at 5.0 by the end of 22. They aim to be up to current standard there as well, and Fortran 18 currently. And again, end of the year, they're aiming to bring up to current standard. In terms of things like OpenACC, I think we're currently at support for 2.7, and that's both for AMD and NVIDIA GPUs via our Fortran compiler. And they are actively working on this. Roughly middle of the year, I think they're aiming to be at 3.0 support, and we do plan ongoing support for newer OpenACC versions 3.1 and beyond. So this is the big picture overview of everything in the environment. In terms of the advantages of our environment, it's really a focus on performance and programmability. So we focus on quite aggressive optimization in the CRAY compiler, and we can give you some really nice optimization feedback for application tuning. We provide this consistent environment over a variety of systems and a variety of different architectures. So you may have a lot of different types of hardware in the various systems that we sell, and we have one environment that covers most of these and can give you a reasonable level of support. We have the integration with visualization and parallelization tools, and this strong focus on portability through our language support, our programming model support, et cetera, et cetera. So CRAY MPI is one of the cornerstones of CPE, and this is, as we say, designed to deliver performance for HPC applications at scale. And so CRAY MPI is derived from MPICH, which was implementation of MPI 3, started by Argonne, I believe. And this is highly optimized for your high-speed interconnect. And so the CRAY MPI library is optimized for very low latency and high bandwidth, both on and off node, for point-to-point and collective communication. And this is typically able to take advantage of the network and GPU accelerator blades with GPU to GPU transfers, this type of thing. You also have CRAY SHMEM, which gives you a lightweight, one-sided access to the high-speed network. And this conforms to the Open SHMEM 1.0 spec. So we have a variety of scientific and math libraries. There's, of course, sort of on-node performance, so BLAST, some of the other libraries, sorry, some of the other libraries I mentioned earlier. And really one of the main benefits of this collection is that it includes tools designed to take full advantage of the underlying hardware. So there's a lot of optimization work that's been done in these libraries for specific types of CPU. They use auto tuning and adaptation so that you get as good a performance as we can give for a variety of codes at runtime. And we give the simple interfaces into quite complex software. These libraries are easy to use with a variety of compilers. So I mentioned earlier the compiler wrappers. You can swap. We have a simple module system which you use to swap between different programming environments. So we have an example line here swapping between the GNU and the CRAY programming environments. And you can see the types of modules that are listed. And when you use our compiler wrappers, we see the CRAY Clang compiler, and then with a simple module swap back to GNU, now we have GCC. And when you build your code using our compiler wrapper, you automatically get the appropriate library and header files to use some of our high performance libraries. Now, in terms of debugging tools, we have a variety of tools available in CPE. So we have for analyzing your program when it's crashed, we have the stack trace analysis tool and ATP, and these can really help in determining why exactly your program has crashed. And we have a variety of scalable debugging tools. So we have a comparative debugger, which has a GUI that allows you to compare data structures between multiple executing applications, try and detect issues. This is called CCDB. We also have debuggers based on a debugger based on GDB, which I'll talk about more in a moment, and Valgrind as well, where we've extended these sort of well-known tools to be more applicable to supercomputing environments, so highly parallel, lots of processes running. That was not so easy with the original versions of these tools. We also support traditional debuggers via third-party tools, so TotalView and DDT. So GDB for HPC, and the point here is that debugging at scale is difficult, and GDB is a well-used tool for debugging on HPC systems that many people know well, but it was quite difficult to work with when you have many processes. And so HPE have this tool we call GDB for HPC that's available within CPE that allows you to analyze your code when it's running on many threads and many processing elements, and helps you with sort of attaching GDB to multiple processes, communicating with GDB, and viewing or inspecting your program contents at runtime. And so the example here is that if you print this variable NPE and it's the same on all of your processes, then we can simply see your process set on 128 processes here all have the value 128 for NPE. Whereas for a separate value JMax, which actually differs, then we see two different process sets and the different value that they have. And so we glue all this together with a communication tree, and you can, like normal, you can just simply launch an application or attach to an already running application and have a simpler way of debugging your program via GDB in the highly parallel case. And this supports multiple compilers, languages, and programming models that we support within CCE. We have a variety of performance analysis tools. So I mentioned the visualization tool and the code parallelization assistant. And these are really quite helpful at profiling at scale. And so I see here over 256,000 ranks we've profiled successfully with these tools, and they really are designed to collect together the information that we can gather with our performance analysis API and present this to you in a way that is both understandable and gives you suggestions on how you can improve your performance and identify things like load imbalance and this type of thing. So perf tools is the way that we can analyze program performance, and this is how we gather the information that we display in the visualization tool. And this is a really simple way of gathering some initial performance results. And in the simple case, you can just module load perf tools lite, build your application, and run it, and then you'll automatically have a bunch of performance information gathered and given to you in the form of a text-based report and a file that you can then open up in the visualization tool. And you can get timeline views of your application run. You can see all sorts of things that are happening, and you can get insights to try and improve the performance of your application. We can profile, so we support sampling, tracing, and trace enhanced sampling in both C, C++, and Fortran, and this integrates with most of the programming models we support, both for host, GPU, and distributed memory programming. So that's CUDA, HIP, MPI, OpenAC, OpenMP, the offload part, 2, SHMEM, UPC, etc., etc. We allow you to instrument your code both at a function level and more fine-grained using a tracing API, and we can capture and present a reasonable amount of GPU info, kernel execution time, data transfers, this type of thing, host device interactions, and present this in a timeline so you can correlate activity between your host, your device, and your MPI runtime. And so this is what's available. In the simple case, you also have a more advanced interface where you can do a lot more tuning of exactly what you want to analyze beyond this just Powerful Tools Lite output. So as an example of some of the guidance that we can provide, this includes things like MPI grid detection. So Powerful Tools here can recognize that you're doing point-to-point MPI communication in a particular grid pattern, and provide some helpful guidance for performance optimization. So here, once we detect this grid-based communication, we can suggest rank orderings to try and maximize your in-node communication and move ranks that are doing most communication onto similar nodes, so that the communication doesn't have to travel so far. Our code parallelization assistant tool combines your performance statistics and your program source code visualization with the optimization feedback that our compiler provides, and allows you to improve your application performance with inserting OpenMP pragmas where appropriate, etc. And this tries to bring together the different types of performance analysis and optimization hints that we can provide, and give you a GUI where you can see these and identify good spots in the program, particularly for things like first moving a code to GPU and identifying work-intensive loops and do dependence analysis and this type of thing. So this covers most of what's available in CPE at a very high level. So to summarize, this is our scalable software stack for programming a variety of architectures available in HPE and HPE CRAY systems. We integrate very well with different vendor tool chains, and we have a very strong focus on helping users achieve scalable performance, portability, and programmability for HPC applications across architectures. And this has been, as I said, a super quick introduction at a very high level. And as Owen said, there is some ongoing collaboration with HPE on this, so we are happy to work further with the Materials and Molecular Modeling Hub and UCL on perhaps more detailed overviews of some of these tools, demos, and this type of thing, if people would like. But for now, that's everything. And yeah, my email's there if anyone has any questions afterwards. Feel free to just shoot me an email.